All right. So we're going to talk about arc length today. And I think I've figured that right before we'll finish chapter 6 before spring break. So that Friday before spring break, we will have chapter 6 test. So yay. So arc length is actually going to look a lot like the distance formula. So let's get into it. So the arc length formula, if we have a smooth curve with parametric equations, remember a parametric equation, our x coordinate is defined by some function in terms of t, and our y coordinate is defined by a different function in terms of t. So we have x equals f of t and y equals g of t, where t is some value between a and b. And we traverse that curve exactly one time. So we go from one end to the other, and that's it. As t increases from a to b, then its length is the integral from a to b of the derivative of x with respect to t squared plus the derivative of y with respect to t squared, and then that whole thing is under the square root. So another way that you could write this is it's the square root of f prime of t squared plus g prime of t squared. The reason I say it resembles the distance formula is x2 minus x1 squared plus y2 minus y1 squared, and then take the square root. It's the change in x squared plus the change in y squared, and take the square root. So the fact that we're doing this with a curve is why we can't, it's not a straight line distance, but that's where the integral comes in very handy. All right, so let's take a look at the length of an arc of the curve from, the curve is x equals t squared, y equals t cubed, between the points 1, 1 and 4, 8. So, we're given our x and y coordinates, but we need to know our value for t in this case to give us the points 1, 1 and 4, 8. And so if you look, the values for t, that when I square it would give me 1, and if I cube it, it would give me 1. So I think that the lower limit, this first point, comes when t is equal to 1. Right, because 1, let's not erase, here we go. 1 would have to equal t squared, and at the same time, 1 has to equal t cubed. So this could be positive or negative 1, but this one has to be positive 1. So I can eliminate the the negative. And then the same thing for the second point. T squared has to be 4. T cubed has to be 8. Again, we could get positive or negative 2. But when I look at the y part, that can only be positive 2. So we can forget about the negative. So we've got our limits. We're going to go from 1 to 2. So the length of our curve is going to go from 1 to 2. We're going to get the square root. The derivative of x with respect to t. Now let's see, that would be 2t. And I'm going to square it. Plus the derivative of y with respect to t. 3t squared. And I'm going to square that. Four t squared plus 9t to the 4th. All right, now to integrate. Well, before I integrate, what I'm going to do, I see a common factor there of t squared. And then the fact that I have a product underneath the square root symbol, I can actually take the square root of t squared and the square root of 4 plus 9t squared. See, the square root of t squared is just t. And then I still have 4 plus 9t squared underneath my second radical. Or underneath the radical, I should say. Now I have a composite function times this other function. So there are usually two choices when we get to this point. Either it's going to be integration by parts, or it's going to be substitution. The nice thing is for this one, it's substitution. So just when you thought you would never see substitution again. So our u is going to be our part underneath the square root. The derivative is 18t dt. I have the t and the dt. So I'm going to divide by 18 here and get 1 over 18 du is equal to t dt. I'm also going to change my limits so they're in terms of u instead of t. So my lower limit, which was 1, is now going to be 13. And my upper limit, which was 2, is now, let's see, 2 squared is 4. 4 times 9 is 36. 36 plus 4 is 40. So if I use substitution, I'm going to get that 1 over 18. I'm going to write that out front. My limits changed to 13 and 40. My t dt becomes my du, and 4 plus 9t squared becomes my u, but that's still underneath the square root symbol, so we have 1/2 u to the 1/2. Excuse me. And now I can integrate. U to the 1/2. Well, I add 1, so I get u to the 3/2. And 2/3. A little bit of cancellation. So that's 1 over 27. 40 to the 3/2 minus 13 to the 3/2. Now, if you want to get really creative, this would be 40 root 40 minus 13 root 13 all over 27. And yes, there's a factor that can come up out. This is a great answer. This is a great answer. You could use a decimal approximation as well, which hopefully you've learned by now. I'm not big on using decimal approximations. But you could, again, round it to 3 decimal places for your answer. So if your function is defined parametrically, that's kind of the approach. But functions don't have to be defined parametrically. So if we have functions defined explicitly, y equals a function of x, then instead of the integral of the square root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared, basically you're looking at the square root of 1. And one way to think about that, that's the derivative of x with respect to x. Dx over dx is 1. And we could put squared in there. Nothing wrong with that because 1 squared is 1. But then we take the derivative with respect to derivative of y with respect to x and square that and take the square root. If it's x equals a function of y, then it's just the derivative of x with respect to y squared plus 1. Again, if you want to think of that still being squared to keep the formula consistent, you could, and then take the square root. Usually, if we have one of these forms, we are not going to be able to find the integral exactly. We would have to estimate using the trapezoidal rule or Simpson's rule or left-hand endpoints or right-hand endpoints or midpoints or one of those formulas to estimate the integral. Because that constant of 1 can cause some issues. Not always. You can cook up an example where it works out. We'll take a look at one. Oh, so on the AP exam, you won't have to worry about tables of integrals. They could say use Simpson's rule. They could say use the trapezoidal rule. If it's on the calculator portion, you can always use the FN int on your calculator. What is that? Math option number 9 is always a possibility. So estimate the length of the portion of the hyperbola x times y equals 1 from the point 1, 1 to the point 2, 1/2. All right, so the first thing I would do is solve that equation either for x or y. Out of convention, I always solve it for y. Notice it says estimate, so we're not going to be able to find this exactly. For my formula, I know I'm going to take the integral then from a to b of 1 plus dy over dx squared and take the square root. So I do need to find my derivative. So if I think of 1 over x as x to the negative first, its derivative, I take the negative, bring it down, take x to 1 less power. So now I have my arc length is the integral. Because I'm in terms of x, I use my x coordinates. Square root 1 plus negative x to the negative second squared. I'm just going to write it that way. 1 over x to the fourth. The negative, when I square it, the negative in front becomes positive. Hopefully that makes sense. But we don't have a way to calculate that, that integral directly. So we're going to estimate. So a couple of options. I'm going to stop sharing just for a second. So one option would be to use our calculator. So we could go to the calculator. Do fn int from 1 to 2. My function is the square root of 1 plus 1 divided by x to the fourth in terms of x. And it will take the calculator a minute to, not a minute, but a little bit of time to calculate that. Well, I guess maybe not a lot of time. A little bit is about right, to come up with that approximation. So I believe the calculator uses Simpson's rule to calculate these integrals. So you could certainly do it that way. 1.132 rounded to 3 decimal places. That would work. You could also use Simpson's rule. So you would have your delta x would be 2 minus 1. Let's go with 10 subintervals. And Simpson's rule with 10 subintervals would be our delta x divided by 3. And I'm just going to plug the values in. So it would be the square root of 1 plus 1 over 1 to the 4th plus 4 times the square root of 1 plus 1 over 1.1 to the 4th plus 2 times the square root of 1 plus 1 over 1.2 to the 4th plus 4 times the square root of 1 plus 1 plus 1 over 1.3 to the 4th, and so on, until I end with 4 square root 1 plus 1 over 1.9 to the 4th plus the square root of 1 plus 1 over 2 to the 4th. And again, we're going to come up with that same approximation to 3 decimal places. If you don't believe me, I invite you to go ahead and calculate that on your own. I'm kind of like the using the calculator, a little less work. And yes, on the AP exam, on the calculator portion, you can certainly use your calculator to evaluate an integral. You can also use it to evaluate a derivative. But what you would want to do is make sure you write, this is the integral that I'm evaluating, and then you can just put the answer in from your calculator. You don't have to show the actual integration if it's on the calculator portion. Big assignment today. I believe they all are, you can find each of those answers exactly. You don't need to do any approximating, I think. Oh, I lied. Okay. So 4 and 5, it asks you to set up the integral and then use your calculator. And they want them rounded to 4 decimal places for both 4 and 5. 7 and 9, you can find the exact length of the curve. So there will be no need to approximate the last two.